thank you, Jim. Thank you, Susan. Thank you for everybody for really making me feel at home these last couple of days. Really enjoyed it. And yeah, I often, if it wasn't for Jim and Susan, I'd probably still be at Vanderbilt with my trying to finish my dissertation. Jim was generous. It wasn't 5 years. It was closer to 7. So, whatever. But amazing, as he said, mentorship and colleagueship and friendship and very much family. So today I want to accomplish hopefully a couple of different things. Start off with maybe a brief introduction, some overview of maybe some broad interest areas that I have, and that may take a little bit more than 5 minutes, but more or less. Then try and get into the modeling and look at some overview of modeling in STEM education, and then specifically a couple of studies and projects that I've been personally involved with, including data modeling as an introduction to experiment, use of physical, symbolic, and computational modeling with middle school students and teachers, and then the most recent project that I have, a currently funded project with other colleagues I'll talk about, cloud-based computing in STEM education. So kind of touch upon kind of 3 different areas of what I think are modeling in STEM education, and with a little introduction on some of the other types of things that I've been involved with. So as Jim has indicated, I had some K-12 experience, a couple of years at St. Anthony's High School in Jersey City, where I was a dean of students and a science teacher, 4 years at Hoboken High, and various certificates. I found out when I went back there, I'm one of the last people who actually have this kind of K-12 all-inclusive science education certificate in New Jersey. So evidently they think I can teach science from kindergarten through 12th grade. I was also, as I said, the assistant superintendent of schools. While I was over there, oversaw the conception and development and editing of a pre-K to 12 curriculum. It was the first time in 25 years that curriculum had been re-envisioned or even reimagined in the district. Basically worked with about a $63 million budget over those years. Oversaw about 8,000 hours of professional development with 80 district teachers over that time period. So there was a professional development, and then we would develop the curriculum. So it was like a bottom-up approach to curriculum development with professional oversight. So we would have like learning scientists and other colleagues like look over what was being developed. Formed partnerships with the Liberty Science Center, New Jersey Commission on Holocaust Education, the National Center for History, schools, Historical Museum in Hoboken, National Geographic, etc. So really tried to broaden the idea of what it would mean to create a curriculum at a district level. And Hoboken was a nice size. Hoboken was a 1 feeder system district, if you kind of know what that means. You basically had 4 grammar schools feeding into 2 middle schools, feeding into 1 high school. So very manageable, kind of like administratively and conceptually, so it wasn't too complicated of a place. And brought things like tools of the mind, which is kind of a Vygotsky approach to pre-K education, Read 180, SRI, John Hopkins program, etc. So a lot of fun. I think the thing I most enjoyed about it was like you could actually think about doing something and it could get done like in about a week or 2. And it sometimes academia moves a little slower than that, and so while I was there, I wanted to do a language program in the schools. Long story short, that was rejected kind of politically. Ended up being a founder of a dual language charter school in Hoboken. It's now a model dual language program in New Jersey, Department of Education, recognized for the last 3 years independently as a model dual language program. It was the first public dual language school in New Jersey. It's top 10% of public schools in New Jersey. Literally was constructing it. As we would expand classrooms, we would build parts of it. There's the kind of broader community. This is symbolic. This is lottery kind of earned. We were the first school in New Jersey to actually use a lottery system, a weighted lottery for students to get into the school. So every charter school, every school that has a program where you have more applicants than seats, you have to have a lottery. We instituted a weighted lottery, which gave further weight to underrepresented populations. And we were the first ones to get that officially sanctioned, and now that's become pretty much policy in New Jersey. So proud of initiating that. Part of that was building advocacy. So these 4 people you see who are obviously, strangers to all of you. This is a Board of Ed member from the Hoboken Public Schools. This was the principal of the school. This was a freeholder. And this was a board member of OLA. And this was the kind of people you needed to bring together to build community in a city and to build community to have like a successful school, both politically and administratively. Just an example of kind of the fun and the enjoyment that I had of bringing some of these people together. Complementary to that, in Austin, I'm involved with the UT Elementary School, which is a local charter school that was started at the university, and been a member of that for quite a while. As Jim indicated, quickly, my own background, my graduate work, did a master's at Teachers College while I was still teaching in Hoboken, then Vanderbilt, and then a postdoc at Wisconsin, where I was a postdoc with the McDonald Foundation and was part of, fortunate enough to be part of the National Center of Assessment in Math and Science. One thing I'm very happy about are doctoral students that I was fortunate enough to mentor and kind of become some legacy. And these are my students. We've got Todd is at Alabama, and Christina is a director of a science center in Bend. Candace Walkington at SMU. Margaret Lucero's at Santa Clara. Vanessa Sfila, some of you may know, in Learning Sciences. Bashkar at Minnesota, Joey Offers at Austin Community College, and David Carrero is an assistant dean out at El Paso. So, not to make you feel a little bit older than former students who are now deans. So, quick overview. I think I'm doing okay so far on some areas of research that I have done, just to kind of maybe fill in some areas. So informal museum learning, done work at the Children's Museum in Minneapolis, where we kind of looked at docents. St. Louis Science Center with actually Jim and Susan as part of the Schools for Thought program, years ago, where we were trying to institute some of the components of anchored instruction and communication through various technology programs. I've done work with the Texas Memorial Museum. Port Aransas, Texas, UT has a satellite there, and we've taken students out on the Gulf. It's part of my courses and part of my research projects, kind of an informal learning science area there. That was successful enough that program led to funding by UT to create a basic ecosystem and dorms for students to come and visit that area, and they use that now continually as part of a kind of field-based component for classes. Liberty Science Center over New Jersey, and I've taught a number of courses on informal learning and museum learning while at UT. Done some work on, so understanding natural selection in the learning sciences. Basic component there, and I apologize for this, but so look at this idea of natural selection. We look at things like variation, inheritance, deep time, randomness, decentralized mindset as components of what is necessary to have an understanding of natural selection or evolution. I purposely don't get into beliefs, okay? I'd look at it from a perspective of what are the concepts that we need to understand to get some comprehension about what's involved with evolution. The basic presumption there is that believing in evolution without understanding it is not necessarily anything that I would really want to like strive for either. Believing it or not believing it. Try to have students understand it, and then they could reach their own decisions. And that course is quite interesting. I teach about once every other year lately. And I said that's led to a couple of publications, including one in JARS that came out last year, and another one where we developed a concept inventory in evolution. So that's been a little strand that's been going on for a couple of years now. As Jim had indicated before, bioengineering and the VANT grant adopted how people learn principles. I led a K through 12 initiative with some additional funding. We did extensive REU components, research experience for undergrads, and a RET program, research experience for teachers. I had kind of sub awards off of that. I thought might be interesting to you. The grant lasted about 7 or 8 years, had 4 main thrusts: the domain specificity of bioengineering, learning technologies, assessment and evaluation, and then of course the learning sciences and the interaction. And one of the best professional experiences of my life was like being involved in this project. It was really a lot of fun. We created some next generation of learning materials. Some of these materials are still being used in biomedical engineering at Austin anyway, I know that. It led to the building of an actual, not only a degree program, but actually a biomedical engineering building, which is not easy to do on campus, as many of you know. Created a number of biomechanics engineering modules, including jumping jack, iron cross, other types of environments. These were done in collaboration with other colleagues. Sean Brophy at Purdue, for instance. Marcus Pandy, who was at UT at the time. Did a number of research projects off of this. We got some good, I think, classroom-based research. This was data that I think was accumulated by David Cordray at one point, to showing kind of the effect size and the cohorts of some of the modules that we created and implemented with biomechanical engineers and biomedical engineers at Vanderbilt and UT, Northwestern. A little aside, like talking about learning sciences, when we would go and kind of talk to some of the biomedical engineers at UT. And I remember going to some of those meetings and trying to explain to some of the professors what we were trying to do with the learning sciences. And they weren't always completely embracing of the idea that we were trying to impart some ideas that we had learned from working with students in middle school or high school at the college level, and so there was a lot of negotiation over time and community building there too, but that worked out very well over time. And having learning scientists like Jim involved were very critical to that. Some of you may the legacy cycle, that was kind of a core component of a lot of the materials that were built at the time. Worked with, like I said, Austin and San Antonio, as well as looking at the content from learning sciences. Vanessa and I and Manu kind of at this adaptive expertise was one of the things that we were looking at, and we come up with some rubrics of looking at expertise as a combination of factual knowledge, conceptual knowledge, and transfer. That's the F, the C, and the T. And there's a couple of manuscripts and papers floating around about this where, that those numbers give a false impression of accuracy there, but it's probably at least in that order. What separated like kind of the novices and the experts seemed to be not as much factual information, not as much conceptual, but the ability to solve problems in novel settings really seemed to kind of distinguish. And that's kind of held up in a couple of different studies that we've done. So that work I'm particularly happy with, but finding a difficult place to call home with that work. Also came together with an edited volume of all the work, or a fair amount of the work that came out of the VANT project. This was a publication, I think it came out in 2007 to 2008, developing student expertise and community lessons from how people learn. And these were chapters that emanated from the VANT project. And it got some nice reviews and still, I think, fairly popular journal for the kind of in the new directions in teaching and learning. If you have questions, I'm fine answering them as we go on. I don't know exactly how, but fairly. This integration of technology and pre-service teacher ed. This is one of the latest projects that I've been involved with a graduate student of mine, Jason Heron. We're kind of using Google Glasses and working around. So these are pictures of the Texas Memorial Museum, and this is what students look through with their Google Glasses, and they're able to kind of navigate around the museum virtually in this kind of VR environment. You see them up there in the upper left-hand corner. Those are pre-service elementary science students. And what you see here are these kind of visual representations, or they look like heat maps, right, of what they're paying attention to. So we're able to kind of get the data that they're using as they navigate through the Google Glasses, which are designed just to be used with a common cell phone. So there's no real special equipment. The Google Glass themselves, I think, cost about $20. They're made cardboard and some glass lenses. You can kind of put your cell phone in there and navigate just using the kind of knob. So it's low expense, purposely designed to be low expense, so it could be used in schools. Right? We could have got maybe more fancy. We tried to go consciously with the less expensive models that maybe actually could be used in schools. And then what you can see, we've got the technology down and techniques now where we could kind of actually tell like what types of exhibits they're paying attention to, they're spending time on. The red obviously is where it's more, the yellow, green, a little less, and the blue less than that. So these turn out to be some of the dinosaur exhibits. These turn out to be some of the gems and geology. We're following up with some more extensive studies of this with maybe a think aloud protocols and following them and looking a little bit more closely at what they're doing. And we've got a study that's coming out where we got some reviews back where we do the virtual first, and then they actually go to the museum, and then they go to the museum, and then they do the virtual. So we're kind of seeing what we get out of that.
So when they're sitting in that classroom looking like, or even in the real world, is there one particular place that they enter into that hall or into the first floor, or are there multiple places that you can
They enter like the front door, like what? Yeah, okay. yeah, and it takes you to the main. It's the main hall where everyone who goes into the museum enters through there, and then there's a couple of doorways that you go, and it's floors. There's one floor below and two above. Another area that I've done a little bit of work on of late is this children's science book database, created with a couple of some help at the university with the Office of Instructional Innovation. Basically, kind of create a review template that encourages pre-service teachers to engage critically with the texts in terms of their scientific content, fostering scientific process skills. So we basically read children's books, and then there's a series of questions that are designed for them to be kind of reflective about The content, the realistic aspects, what reading level, appropriate for class or not, because what is happening in Texas anyway is that science is basically pretty much not being taught at any level before fifth grade because testing begins around the fifth grade. So what they're often asked to do is do reading in science or do math in science and try to figure out some ways to kind of push a little more science into kind of like the reading instruction. And this has been something that we've had a little fun developing, and it's now being used extensively in that program. Pre-service teachers are asked research questions. They critically assess the literature for processes, content, readability, engagement, and interest. I got a link to the database, but I'll share that if people want to take a look at it. Okay. So that's a little overview in some areas. We'll talk a little bit about modeling now. Are there any questions of anything that's come before or comments? So I saw this little.
One quick question about those heat maps.
Yep.
Are those individual students or is it
That's collective, but we could do it either way. The ones that you're seeing there are group, but we could easily do it by individual.
Because I wonder, about where the largest area of red, right, is essentially right where they enter.
Mm-hmm.
I don't know for sure, but both the two floors, right, people seem to be stuck right at the beginning, at the entrance, maybe trying to figure out where they're going.
Right.
But as you and I talk, understanding what these reflect is going to require some additional signal outs or whatever.
Yes. Right. Yeah. And even mapping exactly where these are, that's in the paper, like where these red zones are, like what exhibits they are, but like you said, part of it is like you said, just walking in and navigating and figuring out where they want to go. But after you get through these, these are like kind of the hallways, right? These are the stairways. The exhibits themselves, you do get some variation of them. Yes.
So based off of those heat maps, did you notice that the students would usually stick together in groups, or would they kind of separate off?
So, not based on the heat maps, because we haven't done that analysis because that's what it looks like. We don't know where they, but like from the visits of the museum, they kind of separate. They go into like groups of 2 or 3.
Because sometimes, they want to be with their friends or something,
yeah.
So they might just stick with each other rather than see something that they would, want to see, for example.
But when they're doing it virtually, like up there, they're doing it individually.
Right.
There's nobody else in the space. No. It's just them moving through the space.
They don't know where anybody is. So that's individual. Like I said, we could disaggregate that by individual or by group. They seem to last about 5 minutes doing that, and then they have they got to take a rest, or some of them get a little dizzy. So we learned a little bit about that too. So it seems to be a pretty intense experience navigating that. So modeling in STEM education, I like this. This is a 2-minute video, and maybe kind of set things up a little bit, and it might be some people familiar, but
when I think about modeling, I think about describing how phenomena work. And so some things that are called modeling, which they are models. You would say, for example, a 3D structural model. That's a model of something. But there's not a lot of information necessarily there in how that thing works. And so when I think about modeling, I'm always thinking about something that has explanatory and predictive value. To bring modeling into classrooms means what we want to do is we want to help kids develop these scientific models to explain the world. Not from scratch, with lots of careful guidance, by carefully sequencing the kinds of phenomena and questions that we raise about those phenomena. All models have limitations, and so no models ever perfect. And what students do when they're debating back and forth about modeling their various models that they have is they're pushing each other's boundaries of what are the limitations of a model. How is that model going to work to explain the phenomena that we see before us, and how might we apply that to some new ideas or related phenomena?
So, when scientists use models, obviously their models are always tentative, and much of their interactions with their peers revolves around, the ability of their models to predict and explain the phenomena that they're interested in, right? And whose model maybe does that slightly more effectively or whatever. And so over time, through this community process, through a whole network of scientists, we arrive at more predictive and more powerful models that help us understand our world better.
And so I think modeling is a key practice that all scientists do, and that for us to not include that as an everyday kind of experience in science classrooms would do a disservice to our students.
Okay. So what I want to try to show with the purpose of that little introduction is to show in ways that I hope some of my work has tried to make modeling an everyday practice in a number of different settings. So I'm going to talk to you about a couple of different projects that have gone on or are going on, and I think all of them share some sense of trying to make modeling more of an everyday practice in the classroom, both for teachers and as well as for students. So if we look at an overview of modeling STEM education from a philosophy of science, abstract objects constructed in conformity with appropriate general principles and specific conditions. Lesh and Dora talk about more from the learning science. Models are conceptual systems that are expressed using external notation systems that are used to construct, describe, or explain the behaviors of other systems, perhaps so that the other system can be manipulated or predicted intelligently. So I'm going to look at some kids trying to make sense of data representations through data modeling. We're going to look a little bit at trying to make some sense of modeling through physical, symbolic, and computational models of ecosystems, and then we're going to look at some modeling in an agent-based computer environment for the next couple of minutes. So it's very rooted in the reform-based literature from NRC and NGSS. Modeling can begin in the earliest grades with students, models progressing from concrete pictures and or physical scale models to make abstract representations. So I believe it's a core component of NGSS. I believe it's a core component of many of the reform efforts going on in science education also, I think in the learning sciences in general. I don't know whether it's, still working its way into actual classroom practice. Work that I find particularly interesting in this or framing is by Mark Winchell from Washington. And I won't go over this too much in detail, but it'll be available in the slides. He looks at kind of inquiry as practice as opposed to model-based inquiry, and looks across 5 different areas. So scientific knowledge as testable, scientific knowledge is revisable, scientific knowledge is explanatory, it's conjectural, and that it's generative. All right, so on the left is a perspective. Again, I wouldn't dismiss it as being like the stated that it's so common anyway. But the way it's looked at through inquiry, and maybe the way that it would be looked at through model-based reasoning. And so we'll see, hopefully, over the next couple of presentations, ideas in the form of models are tested and revised. They're used to evaluate hypotheses. We see patterns in data. I'd argue that we even make patterns in data sometimes by how we choose to represent them. And we'll see how kids kind of do that. So first area I'd like to talk about is, and I'm going to shoot for being done at 2 o'clock. Is that about right?
Yeah, but we have time.
Yeah.
We have plenty of time to go beyond that in terms of Q&A.
Okay. Good. So I'm going to talk about data modeling and project investigations. This work kind of dates back origins of it, maybe even back to some of the dissertation work I did with model rockets and kids. You know, the typical, you know, shooting the rockets off, typical hands-on activity, common in many schools, right? Popular in informal settings, motivating.
4, 3, 2, 1.
Okay, and that's a model rocket activity at a school. You get a lot of attention for doing this stuff. You get on TV during Space Week. But what happens if we ask the kids a couple of questions? So basically asking, how high did the rocket go? Not an outlandish question to ask if you're launching rockets, right?
Well, I think it was not. I sort of think it went close to the clouds. I guess about, we had 9,000.
Okay, and now his friend comes along.
Yeah, I think it went 1,000 feet.
How do you know that?
It went really high. It stinks when it got soft.
So maybe not as exemplary as we might want to make it out to be. So again, you look at something like this and you know things got to change. So how do we start thinking about how to change? My dissertation work, and again, you know, development of a project, scaffolding of student activity, opportunities to reflect and revise, use of tools, etc. That led to some findings that these experimentation skills increase with the opportunity to give students opportunity to reflect and revise, basically do multiple launches, ask them some questions about it going on, give them some tools to use, and all of a sudden you have like a fairly, you know, kind of nice project going on. And then students' perceptions of their learning environments were more constructivist in nature, using the classroom learning environment survey. So this was also a place that they were more engaged in, at least by self-assessments than by teacher assessments. So very good, right? But what do children do with all the data that they collect? So they're being asked to measure these rockets. As you might guess, that basically use a simple average procedure. What do we mean? Then what becomes typical? And ultimately, with the idea of when is a difference really a difference? Or when is it just a matter of variability, right? So you launch 2 rockets of the same design, they're not going to go exactly the same height, right? So you have some natural variability there. But what if the designs maybe lend toward different features, maybe aerodynamics, and you deal with like rounded cone versus pointed cone? So we took a closer look at comparison and understanding variability. And so we take a look at measurement and looked at things like center and spread and symmetry of the data collected when they would measure with their tools how high the rocket went. Talk about distribution of the data, variability of the data, and this all comes under a notion that we call data modeling. And argument being that that's the segue into like experiment, all right? That by doing a certain kind of experiment, we're talking about data modeling and coming up with comparisons. And can we give students, and these students that we're working with were basically 4th graders, 4th or 5th graders, can we give them the tools to engage in experiment, comparison, variability at a productive level? Allowed students to develop questions, considered qualities of measures and the attributes relevant to a question. We looked at the structure of data and make inferences about questions. One of the problems with instruction is that variability is given very little attention in USA K through 12 instruction. Variability is almost, you know, kind of like dismissed. You know, we do these kind of experiments where they're almost independent of the variation of the data. When it's fairly simple, a brief exposure, maybe some statistics, and then no focus on this idea of data modeling, as I had explained before, with the measurement, distribution, and variability. Most of current science instruction fails to push beyond these comparisons of simple outcomes, and tools for understanding about ideas of sampling, distribution, or variability are not readily accessible to students. Teachers stick closely to ideas of investigation. Go a little bit. These investigations share surface features with inquiry, but not its underlying motivations or epistemologies. Okay, and I would argue, for the most part, not these ideas of data modeling. Right, it might be modeling of a certain kind, but not of the data modeling. So, developed a series of tasks and tools to help students think about error, introduce distribution. The goal was to view variability as distribution and not simply as a collection of differences. So you get some error, random error, or systemic error identified as they were measuring the rockets, for instance. Different procedures were using trial by trial variability. So we would use things like, so I use different tools, right? So one was using an AltiTrack that was made of hard plastic, and another was a kind of a paper kind of formation of something that would measure the angle. And the issues of variance caused by tools with different qualities. And so there was more variability with the tool on the left than on the right, having students kind of come to these understandings. We had students measure a flagpole. You can see that's the data. The data on the right is the representation of that student data. We start having them, this is data that they actually collected. So you can imagine they measure the flagpole, they come up with these numbers, and then you ask them, all right, so how high is the flagpole? So you got a problem, right? You got a problem.
Do they know they have a problem?
When they see it,
Oh, do
right?
That's
When
right.
they see it,
Positive, yeah.
and as you would imagine, like there's a couple of strategies they use. So one is to kind of take like the middle number, another one's to take like the one that comes up the most, and even the binning of these numbers, right, in these columns was something that took like a week or two to derive at, because they had different representations of even the data that they were collecting. So, and kind of making that a little shorter than it was. We introduced ideas like the median and the difference from the median, come up with issues of centrality. So we now developed something called like a spread number, and that spread number has a median and is kind of 0.9. We then introduce what we called fake poll data. All right, so we had the original data. This data set kind of looks like the original one. It still has the extremes. It still has the median, but obviously you can see that it's visually skewed differently, right? And so it's more spread out. So we quantify that, and by using those, so now we have ways of comparing distribution through spread number. Students become kind of familiar and facile with that. Give you a real quick, we won't do the same.
The fourth graders in Verona have achieved an amazing goal. They're doing math at a 12th grade level.
They may not be doing calculus equations yet, but when it comes to working with data and explaining terms like standard deviation, they're outperforming many high school
I
kids.
don't know what that means. Mike West has more on just how fourth graders are doing math at such a high level.
Thanks, Ben and Mike. This UW research project uses a hands-on approach to teach math. It allows students to discover math on their own rather than merely memorizing it.
That's Mark Ruffling, the teacher that I worked with.
What does this red line represent?
Katie Hendrickson and the other fourth graders in Mr. Rolling's class have a problem.
My distance from the flagpole has changed.
They need to find the height of their school's flagpole using these tools.
What did you guys decide to call this?
This puzzle, not to mention words like tangent, would scare most adults.
There's trigonometry. That's exactly how we measure the height of the flagpole. We use trigonometry to do it. And in fourth grade.
0.9004.
But unlike trigonometry, this class is fun.
I'll spare you the rest. Popular media, that's how it's portrayed. But the next task was to introduce had a pencil with a ruler, and pass the pencil and the ruler around and ask students to measure it. So, as you might imagine, the measurements were closer together, right? But again, still not exactly the same. And so here's the actual data of the pencil. This is like the pencil data. And now you can imagine how the variability type, kind of changes. And now recall that spread number, right? It's less spread out, right, than the other numbers. So they're getting ways of quantifying these distributions of data, if you will. And then now they can start comparing things like the flagpole data with the pencil data, right? So now they start comparing, we've got ways to compare distributions. This comes into play when we start revisiting that rocket activity that you saw in the beginning where they're just launching. So now we have different types of rockets. We've got a rounded and a pointed, red and blue. We start seeing distribution. We revisit a rounded versus pointed cone activity. Here's a kind of progression of the different representations that the students made during this kind of 6-week intervention. So it starts with kind of, index cards being put on the board and then kind of color-coded based on different design feature, rounded or pointed. That progresses into a chart that starts to look a little more familiar. And then we start, getting those spread numbers and using distributions and seeing where they fall along like these 3 areas to see if we start making decisions as to which design feature actually goes higher, taking into account the variability.
Can I ask you a question?
Yes.
Can you go back to your progression?
This one.
What is why did they change? What's the kind of stimulus to change from the index cards to?
Part of it is to bring out features more saliently than before. So this would be like one rocket launch, right? With now you add a second rocket launch. So now you want to distinguish one from the other. So the students come up with the idea, with a little nudging, of course, right? Like, well, here I've got index cards and one are yellow and one are orange. What do you think we should do? So, it's teacher dependent, right? The teacher is involved with that. And, so they start seeing this and that might be different, we don't know. But they do have some quantitative tools that they've been being taught with data modeling, right? And so you go from the cards now to maybe this kind of representation of it. And then this was introduced obviously by the researchers as a way of kind of like creating almost like kind of a distribution, right? So loosely, and I'll show you with the next slide, I think it comes out a little bit more clearer. See, so what we're trying to model a little bit, right, is the normal distribution, right? But we're not saying normal. These are not terminologies that we're using, but this is the association that's going on there. And so now they reach a point, they got to make a decision, right? The rounded versus the pointed cones, and now they have some data, they got ways of representing it. They've got ways of thinking about variability. And so pointed and rounded, which would go higher? Anybody want to take a guess at that? Pointed or rounded? Pointed, 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 rounded. So the rounded goes higher. Has something to do with laminar flow and at speeds of under 100 miles an hour. An egg shape is actually a little bit more aerodynamic than a point. And so this becomes a little counterintuitive, and that becomes kind of fun to talk about with students as well, right? Because now they've got this kind of dissonance going on. This led to a couple of papers. So the original paper, Structuring Error, that's kind of an old paper. But then more recently, I was asked to kind of update some of this work by Rick Duschel, working with teachers, doing this kind of at a larger scale. And so this was a chapter in a book that kind of put together teachers' use of data measurement and data modeling. And then another article that I wrote with one of my students, data modeling for pre-service teachers and everyone else. One of the things that I was being confronted with in many ways myself is that, this was a nice article and, got some, little attention, but it was impossible, I thought, to use that article with my pre-service teachers or with the teachers I was working with and expect them to, quote unquote, do it. And so I, created these other ones as I think more practitioner, pedagogical oriented, and have had some success with getting that out there. So this is an example of trying to get some of the work that maybe would normally maybe kind of stay in the research literature and get it out a little bit more into the popular practitioner journals.
So this is a question that sort of says in trying to get this into the, what you're doing over there is you're using your knowledge and as a sort of a teacher to sort of scaffold and guide the students in this data modeling process. My question is, how much do you have to do the same thing with pre-service teachers? Because, and it's really a question of what do they actually understand about this whole process of data modeling spread? Because often that is not something that is very well taught at all in all of K-12 education, simply because statistics and distributions is really not a focus of things in the Common Core even.
This article itself is not only for pre-service teachers, but the way it's written is really for all of undergrads, right? So it's pre-service teachers and everyone else, literally meaning everybody else. The first one is a little more focused on teachers, but the way I would answer it, and this is going to sound, I don't intend it to sound the way it probably would sound, but this stuff just doesn't come naturally or via maturation. You suddenly know how to data model. So I don't find that much difference really between working with the 4th and 5th graders and working with other populations.
No.
But that could sound like being a little bit of a I don't mean that they're the same, but unless you worked on this, unless you study this, unless you try to, it just doesn't come naturally to you, right? So it has to be taught. And as Jim kind of indicated, not many students at the undergrad level know about data modeling. That goes for pre-service teachers, and that goes for English majors, and that goes for history majors, and that goes for phys ed majors, and even a fair amount of the STEM majors. So the notion that I'm doing something with 4th graders and somehow, that may be seen as a kind of derogatory, that I might be using some of the same kind of techniques or same type of activities with, and I've done it with superintendents, I've done it with teachers, I've done it with faculty members, I've done it with people who want to teach project-based instruction. I don't find that much difference, in all honesty, okay? But I think that's all because, as Jim indicates, I think the lack of data modeling instruction that goes on, and you don't get it for free. You just don't get it by being around things. So I want to transition now, talk about a little bit different modeling. All right, so that, you can put that in data modeling. This is more modeling in pre-service teacher education and for students, middle school students. So many middle school classrooms are equipped with these three-dimensional models that we talked about in that beginning video, DNA, the Earth, solar system. In classroom, models are typically used to teach a process or a static sense. Next generation, emphasize this. This work is working with two-tier terrariums. So you get basically like these soda bottles, and you kind of put one inside the other. The bottom is aquatic. Okay, so there's water there, and we have some like plants growing. There's a wick, and then the top there's dirt and there's plants, and so there's kind of a neat little complex ecosystem going on, right? And so call that the physical model. Have students draw them and label it, and called diagrammatic, and then we kind of have them work with some computer modeling program, and we work with what we might call computational models. Hook up probes to them, and they start getting graphs like this for things like CO2, right, which has like a little cycle to it. The oxygen remains relatively stable. You can see the temperature variation like during the course of a day. This is modeling in pre-service teacher education. I look at those three. This is explained more in the article. The physical models, I think of them as a progression. I think the physical model is kind of what we normally use as an introduction to models. All right, so if it was hierarchical, I do consider it maybe more basic, but they represent the world through resemblance, right? And obviously often physical resemblance. In the activity described, the physical model is two-tiered ecosystem. There's the symbolic model we talked about before. Those are diagrams that explicitly demonstrate the relationship between the world and the model. And the symbolic models are diagrams students draw. Having the students actually draw them, they attune to certain things. They notice certain things that they may not notice with the physical model, certainly without taking a picture of the physical model. And then finally, we kind of reach, hopefully, most times the computational models where we start using kind of computer programming, Stella, we use some modeling programs where there's a more abstract type of model and often represent the complex entities that interact to produce some of the emergent behavior, whether that's CO2 accumulation, whether that's oxygen, whether that's the temperature that they get over time from the data. So they try to start modeling this. You wouldn't necessarily get that out of the physical model unless you have the probes, et cetera.
In the computational one,
Mm-hmm.
do they have to move from the symbolic to sort of trying to identify what should be in the computational model, or is parts of that given to them? I mean,
a little bit of both. Definitely some of it's happening by what we choose to use the probes for, right? So that's raising attention for things like temperature. If we're taking temperature, now they get the data. We have the CO2 probes, that brings attention to that. So it's being scaffolded or somehow attention is being given by the probes that we use. Try to be responsive to other questions that they may have, computation. So some of them have decided like they want to keep the light out or they want to make modifications to it. But when I use this with the pre-service teachers and when I use this with the students, 6th, 7th, 8th graders, it's usually kind of presented via those, the probes, give them, and then we ask them, all right, now, we see this, how would you model this variation in temperature? Or how would you model the accumulation of CO2 over time? That's where we kind of come up with this progression. And I'll be honest, we don't always reach this level without maybe some push going on. But we strive for it. They also do a blogging activity where they kind of keep track of this activity itself takes about 2 months to do. They look at it, they take measurements, they take narratives, and then they put it in a blog. They make a blog post once a week. So they do journaling or blogging, and I see this as a way of incorporating reflection and revision. Very much like the rocket stuff before, where the multiple launches give you some leverage. So the blogging or the journaling gives you some of that, metacognition and ability to kind of relook at this activity. Students make observations of their models each class period. They enter it into a blog. Blogging serves two purposes. Students use the technology to write about their ecosystems, and they're accessible to other students so they can follow observations in lab groups. And this is kind of what some of their blogs look like. Okay, so these are what the students are kind of writing down. So some of them will take pictures, right? They'll draw, and then they'll have a little description of what they come up with. And this kind of leads, I think, this is done, 2015. But the computational models, we've got to insert them. They don't necessarily come naturally. So we introduced some modeling software, and with the probes, and we started asking them, how would you represent this in a different way? And so we get there.
So where does the notion about oxygen and, the notion of the
Like that.
changes that are going on,
Mhm.
how does that get introduced?
That's coming through. So we introduced this idea of probes, right? And so they're hooked up to computers that will take the temperature, and like maybe continuously. We could calibrate it every hour. So then this is an example of some of the outputs that they receive, that they get.
But are they told that the things to measure in the system are CO2 and O2 and temperature? It's kind of given.
We talk about it. We talk about photosynthesis. So what might be happening on the top?
Right.
What might be happening in the bottom? All right, if that's happening,
Then what?
yeah. So we're not expecting it to be fully derived.
It's guided.
It's definitely guided. It's definitely guided. All right, so that's that. Now, there's a couple articles on all of these. This is the latest project now. So now this is group-based cloud computing, which I think hopefully you'll agree is another version of modeling. This is web deployed. It's participatory, kind of using NetLogo along with some abilities to collaborate with the internet. It's authorable and it's collaborative. Colleagues Uri Walensky is on this at Northwestern. We've got Corey Brady on this at Vanderbilt, and Walter Shoup at University of Massachusetts at Dartmouth. So I'm going to take a couple of minutes and try to explain it as good as I can.
Classroom interactions are often limited to sequences where teachers pose questions and evaluate student responses. Group-based cloud computing has the potential to allow classrooms to engage in greater interactive and immersive learning in a networked setting. Group-based cloud computing, or GBCC, is a shared online environment where students and teachers create and participate in interactive, STEM-focused activities. GBCC is a fully authourable, easy-to-use environment, which builds on the agent-based modeling supported by NetLogo Web and integrates extensions from powerful mathematics and physics engines and an open mapping library. Using any device with a browser, teachers and students can readily create a room of their own.
So I don't know if you saw that, but it could work on your cell phone, it could work on a tablet, it could work on a desktop, it could work on your laptop. So it's very portable.
Using GBCC, students assume roles in participatory simulations about traffic flow, explore and extend models of ecological relationships, and construct and share geometric figures. The GBCC for STEM project encourages teachers and students to participate more fully in socially mediated learning experiences to broaden and deepen interest in STEM. In this biological model, teachers and students simulate how disease is transmitted through a population. The teacher and students have different interfaces. The teacher is able to start and stop the model, while students interact in the simulation through on-screen controls. Students test the effects of changing different variables in the model to see what happens if they adjust the initial number of infected agents, the transmissibility of the disease.
These are elementary science teachers working with the modeling, introducing coding and modeling whether it's like segregation patterns or the vaccination rates.
Or the vaccination rate. This shared experience serves as the basis for rich class discussions about contemporary issues related to vaccines, such as the effects of low vaccination rates in some communities. In this ecological example, students simulate the trophic cascade caused by the reintroduction of wolves to Yellowstone National Park. The cloud-based capabilities of GBCC allow students to share their models and graphs of their data through the class gallery. By clicking on gallery images, students can copy variables and examine the similarities and differences between multiple models.
So that's the big difference if you say like, well, isn't this NetLogo, right? No, it's not NetLogo, because what you could do is actually share your model. You make your model public, and then people can look at your model, modify your model. You could look at other people's model, which is substantially different, than the maybe traditional NetLogo approach, and that is the nature of the collaborative nature of at least this instantiation of it.
GBCC also supports integration with powerful STEM tools like GeoGebra. This model allows for generative exploration of mathematical concepts. Students write linear functions with the same slope, create lines that pass through a specific intercept, and contribute coordinate points, giving rise to emergent solutions. We're currently conducting research using GBCC to build teachers' capacity for ambitious generative teaching practices, and to develop students' understanding of the nature of modeling. The findings from this research will further inform the design of GBCC models and simulations, and help us better understand how students and teachers can benefit from cloud-based collaborative learning.
So that's a little 3-minute video that gets sent off to NSF. But so what we're looking at, and I'll close things up now, like in the next 2-3 minutes. So one is this idea of reintroducing wolves into Yellowstone, and there's that really great little video that was made a couple of years ago. We decided that was really give us some leverage, and we kind of did a little curriculum around that, as well as this kind of like modeling environment about reintroducing wolves into Yellowstone. And the other is this idea of the vaccination issues, which are very much in the public, and lead to a number of issues, especially in Austin. Austin is has the highest education level in Texas, has one of the highest average incomes in Texas, has the lowest vaccination rate in Texas as well. And in fact, the schools in Texas with the highest SES and Montessori schools, for instance, have vaccination rates under 50%. So there's real issues that are going on here, right? And some of them are counterintuitive, right? Some of them go against some notions of what we think as kind of healthy decisions to be making. So this gets into some social consciousness and justice issues and vaccination. So makes for some interesting work. So this is a little bit with the ecosystem with the wolves in Yellowstone. This is teachers, kind of pre-service teachers working with them. Turns out that the height of the aspen trees kind of has a kind of important component to proliferation of more greenery in Yellowstone. So students start to, again, looking at the relationships of this, right? So we're kind of getting into a little bit of the introduction of modeling this. That gets them looking at the code. So if you can see, right, modified line 18 to include, this is their own work. This is the pre-service teacher's work. Modify line 45, should I do that? Set elk to be unable to eat medium or high trees, and what will that do to the tree height over time? You get more involved, so they're playing around now with the text that's going to go into the coding, and they actually end up coding some of this sort of stuff with the vaccination rate. So we propose problems like Austin's vaccination rate. It's about 97%. However, specific school sites range from 100% to the lowest at 40%. You know, and this is actual data. This is, posing a threat to public health, and worked with 40 pre-service teachers. This is a manuscript that's I think coming out soon in technology and science education.
So, excuse me,
Yeah.
Yesterday when we were talking, you said there's a project-based course, and that's part of the You Teach program.
Yes.
Does this happen in that course, or does this happen for all science?
So what we're seeing here, this specifically was in the elementary pre-service teacher education program, but I also use this in the project-based classroom. So there's going to be a couple of groups. One is going to be doing the vaccination one. Now they're going to be doing it at a secondary level, and then we have another one doing the Yellowstone. So in fact, they just implemented this out in the schools, the You Teach students, the project-based students.
One of the reasons I asked you, because you often get the pushback whenever you talk about doing something different in a course, especially in the natural sciences. It's like, oh, but we have all this content to cover, right? Yeah. And so when you do this, it obviously takes longer, right? Because you're doing a whole bunch of stuff. You're not just reading a chapter and not understanding it. You're actually trying to understand something, right? So I wonder how much you get that resistance, whether you have to be doing this with the right pre-service teacher, educators, or... So
what I could tell you is that the students pretty much, it's like this bimodal, they either love doing it or they really don't like doing it.
The students or the teachers of the students? Or both?
The pre-service teachers that I teach kind of separate into those two groups, right? But when we did this out in the schools, when they actually implemented with high school students, they enjoyed it. We worked with one of the cohorts, the elementary cohorts, in the schools themselves with the young kids, like the middle school, like 4th, 5th graders. It weren't out there long enough to kind of really, but they tried it, which was kind of like encouraging. Yeah. I think that's probably just as good, like ending it. This is just some final. So, Leandro is this is one of the schools in Austin. And you can see what they're doing here is like they're actually drawing what would look like that net logo. And they're putting out what they want as, so they want a bar for vaccination. They want a bar for special education. Then I have my own students, my graduate students, my undergrads who are computer science. They work with the teachers, the pre-service teachers, to create these kind of environments, and they work together collaboratively. So it'd be too much of a stretch to have them do it on their own. They couldn't. But working with like some computer science undergrads who the grant, works with, get some nice interaction. So that's one of the models, and I think this is another one for, East Austin population for zone. So this is another the vaccination. And you can see what they're doing here is that it's a kind of it's a diagram of the kind of interactions they want on that logo page, right, of the interaction.